All right, guys. As we get into our second week of lecture, we are going to get into a little bit more chemistry. And so that's really what chapter 2 is going to cover. I'm also going to do attendance just a touch different. I'm still going to consider your quizzes and your homework, but I'm also going to look at attendance as far as whether you really listened or watched the lecture. And so what's going to happen is that throughout the entire lecture, there will be at least one point where I say, here is a code word. And that code word may or may not have anything to do with the lecture itself. But what you're going to do then is you're just going to go into Canvas. I'll have a small little attendance assignment. And all you're going to do is enter that code word. So something very simple just to indicate that you basically watched the lecture and for all intents and purposes, we're in class. So, and I'll make a little video on that and how I want you guys to go about that. So just make sure that you watch that video before you actually go ahead and watch this lecture class. So as we get into chapter 2 then, we are looking at a little bit more chemistry. So one of the things we look at is the basis of chemistry, and that's going to be matter, atoms, elements, and the periodic table. And so one of the first things we have to do really is understand what matter is. And matter is anything that has mass and occupies space. And there are three forms of matter. There's a solid, a liquid, and a gas. Now, as far as the body goes, you can kind of look at these examples. A solid obviously would be something like a bone. Liquid obviously is blood. And then gas is going to be things like oxygen and carbon dioxide. Now, when we look at matter, we have to look at what an atom also is. And an atom is the smallest particle that exhibits the chemical properties of an element, okay? And so when we look at the periodic table, we are looking at the elements that make up that periodic table. Now we have 92 that are naturally occurring elements, and those make up most of matter, or the majority of matter, and they're organized into the periodic table. And so here is an image of kind of the periodic table. Now since I got this image, there have been some updates and some new discoveries on different elements and how they get put in there. I just don't have the updated one in there. But for what we normally talk about, the updates really come down here to the higher atomic number elements, which we don't really necessarily talk about when we talk about the human body. So when we look at the periodic table, there's a lot of information that gets put into each of these boxes. And not only that, but also the location of where they fall into the periodic table makes a big difference. And we'll talk about what this number is, this symbol is, this number is, what these mean as far as the columns and the rows. And we'll talk about those as we kind of move on through this chapter. So the most common elements of the human body are going to be these ones here on the left. We have oxygen, carbon, hydrogen, nitrogen. Those four really make up the biggest section or the biggest amount of the human body. You can see when you add calcium and phosphorus, we're really looking at about 99% of body weight is made up by these six. But if we essentially look at 97%, really is made up of these first four: oxygen, carbon, hydrogen, and nitrogen. But then we also look at some of the minor elements, and this is where we have sulfur, potassium, sodium, chlorine, magnesium, iron, all making up a little bit smaller portion of it, but also all less than 1% of body weight. So when we look at the components of an atom then, and we look at the smaller parts that really don't make up the properties of an element, we look at the subatomic particles, of which there are three. We have neutrons, protons, and electrons. Now, neutrons really have no charge, therefore they are neutral. They do have a mass of which we consider one atomic mass unit, so 1 AMU. We have protons, which also have a mass of 1 AMU. Protons have a positive charge of +1. And then we have electrons. Now, electrons have a negative charge of -1, but if you also look here at their weight, or their mass, I should say, That's 1/1800th the mass of a proton or neutron. So for all intents and purposes, electrons don't have a mass. And so we actually don't give them a mass of any atomic mass units. Now, as far as the location goes, we're going to find that protons and neutrons are going to be found within the nucleus of an atom, whereas electrons we're going to find are in orbitals, and they're going to be located at varying distances from the nucleus region. Okay. Now, when we look at the periodic table, this is going back to the table that we just looked at. There's a lot of stuff on that table that gives us a lot of information. So one, we have the chemical symbol. And the chemical symbol really is unique to each element. It's usually going to be identified by the first letter, sometimes the first letter plus an additional letter, or sometimes it's going to be made up based off of its Latin name. Okay, so for example, the first few are pretty easy and straightforward. We look at hydrogen is H, helium is He. We look at carbon and oxygen, those are C and O. We look at potassium, that's actually K. If we look down to gold, gold is AU. And so we're starting to look at different ways in which not only are we looking at the first letter, in some we're looking at the first and the second letter, but then again, in some chemical symbols really have nothing to do with the actual name so much more it has to do with the Latin name. When we look at the atomic number is the first number or the top number typically in a periodic table. The atomic number is going to represent the number of protons in the atom of an element. Okay, again, it's going to be located above the symbol name. But again, coming back to what it does, I'm actually going to highlight this or underline it at least. The atomic number is the number of protons in an atom of the element. And the atomic number is going to be the elements in which we arrange them in the atomic numbers within the rows. So if we look at the atomic numbers, you're going to see that as we move on further down into the periodic table, all we're doing is just kind of following those atomic numbers. And again, basically looking at the number of protons in the atom of that element. Now, we also have the atomic mass or the atomic weight. And that's going to be the bottom number, where typically we see a number with a decimal point followed by a couple additional digits. And this is going to be the atomic mass or the atomic weight. And what the atomic mass is it's the mass of both the protons and the neutrons. Okay. So now when we talk about atomic mass and atomic weight, technically there's a small little difference. The atomic mass is something that actually shows the total number of protons and the total number of neutrons within the nucleus. And that atomic mass is typically going to be a whole number. When we look at atomic weight, the atomic weight is typically what we see on the periodic table. Even though I know it says here atomic mass is shown below the element symbol on the table, there is a little bit of a difference because the atomic weight really is more the average of all the atomic masses or isotopes that we find in nature. Okay. And so if you want, we can consider that the average atomic mass as well. So I'm going to scroll back just a couple slides here. Let me go ahead and clear that. So if we look at this again, it may be difficult to see on your computer screen, so I apologize about the graphic, but you should have one of these in your book as well, or you can print off one from the internet pretty easily to follow along. But if we look up here, if we look at hydrogen, we can see the number 1 there. That's going to be the atomic number. That's the number of protons that we find within the nucleus. Here we have hydrogen. This is the atomic symbol, that first letter of the element. And then here, I know it's kind of difficult to see. I believe that is 1.008. And so what that is that's going to be the average of all the atomic masses. Okay. Now, an atomic mass can vary. So With hydrogen, we could have an atomic mass of 1, which means we're going to have 1 proton and 0 neutrons. We can have an atomic mass of 2, which means, again, we're going to have 1 proton, but we may have 1 neutron then as well to give us an atomic mass of 2, which, again, if we look at protons and neutrons, each has 1 AMU. But when we take this number down here, whoops, this number is the average of all of those different isotopes, all of those different atomic masses that we have, and they're averaged based on how they occur in nature. So normally what we're going to see then in hydrogen is a hydrogen atom that normally has 1 proton with 0 neutrons. And we'll talk about that as we continue on here. So here's how we kind of determine the number of subatomic particles. When we look at the protons again always are going to equal the atomic number. So we're always going to have that number of that number of protons in an atom. If we change the number of protons in the atom, we've effectively changed the element, okay? Now, when we look at neutrons, the neutron number, that's actually going to equal the atomic mass minus the atomic number, okay? So I believe, I'm kind of going off memory here, I believe oxygen is element number 6. Its atomic weight typically is around 16, or its atomic mass is going to be around 16. That's the common one. So if we take 16 minus 8, the atomic mass minus the atomic number, that's actually going to give us the number 8. And that indicates how many neutrons then we have in that particular nucleus of that particular atom. Again, here we kind of show neutron number equals protons plus neutrons minus protons. And that's what we're really looking at up here. Atomic mass equals protons plus neutrons. Atomic number equals protons, so we subtract that. So I know that's probably a little confusing there. But this right here is basically simplifying this equation, okay? So if we take the neutron number of sodium, okay? Sodium has an atomic mass of 23. It has an atomic number of 11. So this is the number of protons in the atom. This is the number of protons and neutrons. So if we subtract the number of protons, we get the number of neutrons remaining. Now, in order to determine the number of electrons, this is where we have electrons are going to always equal the number of protons. So in sodium, with an atomic number of 11, that means we are going to have 11 electrons, okay? So protons always equal electrons. So now if we look at the way electrons are held within a particular atom, we are looking at the number of shells that this particular atom has, okay? And these energy shells or electron shells basically surround the nucleus. And this is where electrons are stored. Again, remember, neutrons and protons are stored within the nucleus. So each shell has a given energy level, which you're going to see over here. This is kind of a shell model. Each shell holds a limited number of electrons. There's only so many that can be held within each shell. The innermost shell, which you can see me highlighting here, only can contain 2 electrons. The next or the subsequent layers can actually hold 8. But in order to move on to the next level, the innermost levels or innermost shells have to be full or filled first, okay? So if we look at if we look at carbon in particular, carbon's going to be a situation where it really exists in 3 major isotopes. We're going to call them carbon-12, carbon-13, and carbon-14, based on the number of particles or subatomic particles they have within their nucleus. So if we look at the isotopes and what an isotope actually is, An isotope is where we have a different number of atoms in the same element, okay? Or I should say, they're different atoms within the same element. They have the same number of protons and electrons, but the number of neutrons are actually different. This gives them identical chemical characteristics, but they have different atomic masses, okay? So again, they have identical chemical characteristics, but they have different atomic masses. And this also then allows them to kind of interact with different elements slightly differently. So when we look at carbon, again, we said it exists in 3 different isotopes, carbon-12, carbon-13, and carbon-14. And make a note down here. Carbon-12, note how many protons it has. It has 6. Carbon-13, a different isotope, note the number of protons, 6. And carbon-14, again, different isotope, note the number of protons, 6. So it's always going to have 6 protons, which basically means this is the same element. If we look at the number of electrons, again, protons in an atom are always going to equal electrons. So 6 protons, 6 electrons. 6 protons, 6 electrons. 6 protons, 6 electrons. But notice the difference. Notice the number of neutrons in carbon-12, 6. Notice the number of neutrons in carbon-13, 7. And notice the number of neutrons in carbon-14, 8. Okay? And then this is how we fill the energy levels. The first 2 electrons get put in the first energy level. The next 4 electrons fill the second energy level. Because again, in the first energy level, we can have 2 electrons. The second energy level, we can have up to 8. Okay? And again, the same thing is true for carbon-13 and carbon-14. Now again, we look at isotopes and we look at their atomic mass. Now, when we look at that number in the periodic table, that's the weighted average of the atomic masses for all the isotopes that we know of for that particular element. Now, some of our isotopes are radioisotopes. What that means is they actually contain excess neutrons, so that they become a little bit more unstable. All elements with atomic numbers less than 83 have isotopes. Those with numbers 83 and greater have radioisotopes. And so what that means is they lose nuclear components in the form of high energy radiation. And so we're looking at things like alpha particles, beta particles, and gamma rays. These make up the radioisotope component of the elements. So if we look at the isotopes and we look at what half-lives are, so the physical half-life for an isotope is the time for 50% of the radioisotope to become stable, okay? It can vary from a few hours to thousands of years. So for example, here are a few examples of some elements and some isotopes of elements and what their half-lives are. So polonium-215 has a physical half-life of 0.0018 seconds. That's how fast it really breaks down to become more of a stable element or a stable atom. Bismuth-212 becomes stable in 60.5 seconds. Sodium-24, 15 hours. Iodine-131, 8 days. Cobalt-60, 5.26 years. Radium-226, 1,600 years. And then look at this one. Uranium-238 has a half-life. So 50% of the radioisotope becomes stable after 4.5 billion years. So a very overall unstable element. The biological half-life, however, is the time required for half of the radioactive material from a test to be eliminated from the body. And so we see this a lot with contrast that we're using in things like MRIs and CTs, where we have the dye injected and it allows the imaging to actually show up a little bit differently than what it would without some sort of contrast. So if we look at kind of a clinical view of how we use some of this medical imaging in the thyroid gland, we use the iodine radioisotope. And so radioisotopes can be introduced into the body using different medical procedures. And they're going to be used by cells in a similar manner to non-radioisotopes, in that they basically get pulled into the cells. And the benefits or the positives actually is that it allows us to trace products of metabolic reactions that use these particular elements. And so when we look at the thyroid gland, it's actually going to be darker in areas where less radioactive iodine can be taken up. And it's going to be brighter where more iodine is taken up. And it can basically help us to detect different things, such as you can see here, such as a nodule that may be located on the thyroid gland. Now, one of the things that we have to understand is that no matter what radioisotope we're utilizing, when we use different types of radiation, it's always going to cause damage to the cell or to a particular type of cell, regardless of the purpose. It's one of those things that we just weigh the benefits greater than what the negatives are. So as we continue into kind of this utilizing the periodic table, we start to look at the electrons and its energy shells a little bit more. And so in order to understand chemicals and the stability of a particular element, we have to look and understand what the octet rule is. And so we have to understand not only that, but we also have to understand what a valence shell is. So when we look at the periodic table, we have to understand that it's organized into columns based on the number of electrons in the outer shell. And this outer shell is going to be referred to as a valence shell. Okay, let me go ahead and circle this. A valence shell. Now, when we look at column 1A of the periodic table, it's going to show hydrogen, lithium, sodium, and potassium all within that first column. What that means is it has one electron in its outer shell. So again, look at some of the numbers. Hydrogen has an atomic number of 1. Lithium, an atomic number of 3. Sodium, an atomic number of 11. Potassium, an atomic number, I believe, of 19. So when you start to look at these, hydrogen has 1 proton. So it's got 1 proton, or 1 electron, excuse me. So it has 1 electron in its valence shell. Lithium has 3 electrons. So it's going to fill its first innermost shell with 2, and then its second shell is going to have 1. Sodium has 11 electrons. So again, its first shell is going to have 2. Its second shell is looking to be full, and that second shell can have up to 8. And so its third shell gives us or leaves us with 1. And so again, all of these have 1 electron in their outer shell. As we move to the right in the periodic table and we look at the columns, each column has 1 additional electron in its outer shell. Until we finally get all the way to the very far right of the periodic table, we look at that column 8A or VIIIA. Each of these is going to have a full valence shell because, again, the entire outer shell of that element is going to be completely full with electrons. And when you have a full valence shell, you basically have what we consider chemical stability, okay? Because again, every element is always trying to fill its valence shell. And so some of these in that right-handed column, in column 8A, helium, neon, these are chemically inert noble gases, meaning they are full, they really don't react with anything, okay? So if we try to move on here. So if we start looking a little bit more at how things or how these elements start to interact with each other, we start to look at some of the chemical compounds, and we look at these ions and these ionic compounds. And this is where we start adding or comparing bonds together. So chemical compounds are have stable associations between two or more elements that are combined into a fixed ratio. These are going to be classified as ionic or molecular. Okay. Now, ionic compounds are structures that are composed of ions. They're going to be held together in a lattice by ionic bonds. So we really need to look at what ions are and how they create these ionic bonds. So ions are atoms with a positive or a negative charge. Okay. And they're going to be produced from the loss or the gain of one or more electrons. So as they start to move and shift these electrons around, we start to get elements that begin to have a little bit more of a positive charge or a negative charge. And we're going to see these ions are going to be used in a lot of our physiological functions. Okay. So if we look at potassium, for example, potassium typically becomes a more positive ion. It will actually give up an electron, which means it's losing one of its negative charges and becomes positive. And we're going to see that it's going to be used in sports drinks to replace the potassium loss in sweat. However, if we have a large dose or significantly large dose of potassium, we'll actually see that it's partly used in some states that utilize lethal injection because it does affect the electronegativity of the heart and the function of the heart. Now, cations are going to be ions with a positive charge. They're going to lose electrons to other atoms. So sodium can reach stability actually by donating an electron. Again, it becomes a more positive ion by giving one up. If we look at that periodic table, we know that sodium has one extra electron in its valence shell. And so it wants to give that electron up so that its outer shell is full. So it gives it up, it becomes positive, and now it has 11 protons and has 10 electrons, giving it a charge of positive 1. Okay. We also have the opposite. We also have anions. And anions are going to have a negative charge. They have more of a tendency to want to take on an extra electron. So if we look at chlorine, chlorine has, normally anyway, has 17 protons and 17 electrons. It has 7 electrons in its valence shell because, again, we start with 2 in the first one, 8 in the second one, which gives us 10. We have 7 left, so 7 electrons in its valence shell. It takes on 1 more, that gives it 8, which means it has a full valence shell, but we also now have 18 electrons, and so it has a charge of -1. Okay. And so because by doing this, it actually reaches more stability. Now, we also have polyatomic ions, and these are anions with more than one atom. For example, a bicarbonate ion and a phosphate ion. And we'll talk a little bit more about the bicarbonate ion when we talk about buffers, and the phosphate ion a little bit later with ATP. So now that we have kind of the basis of what ions are, now let's look at what ionic bonds are. And so ionic bonds are actually formed by joining together cations and anions, but they're actually bound by the electrostatic forces. And so what we mean by that is think about having a positive side and a negative side. Think about magnets. Positive and negatives come together and join. It's the same thing here. We have a positive cation and negative anion, and so as they come together, they actually are attracted to each other by those opposite forces. Okay. Now, it's at this point that we're not necessarily doing anything with the electrons anymore, but we're using the charge differential. So what we actually do with ionic bonds is we transfer electrons from one ion or one atom to another. And when we do this, what we typically get is salt. And so if we look at table salt, which is NaCl, I'm going to take a step forward here. If we look at table salt, this is going to be NaCl. So we have sodium and chlorine. Each sodium atom is going to lose one of its outer shell electrons to a chlorine ion, or to a chlorine atom. And so that's going to make the sodium ion positive, but because chlorine is taking on an electron, it's going to become more negative. And so now sodium and chlorine ions are then held together by the ionic bonds that are formed from the positive and negative charge of the two individual ions. We also see the same thing with magnesium chloride. Magnesium atom loses one electron to each of the two chlorine ions, and again, we kind of get a salt structure. If we look at sodium chloride, you get a chance to see kind of the chemistry component of what actually occurs. If we look at sodium here we have its valence shell. So again, we have 11 electrons to start with. 2 in the first shell, 8 in the second shell, that gives us 10, and 1 in its valence shell, okay? Chlorine, on the other hand, has 2 in the first, 8 in the second, and 7 in its valence shell. So if we think about how does each of these atoms become a happy atom? By satisfying the octet rule, by satisfying the rule of 8 in its valence shell. Well, sodium would give 1 up, which means now this valence shell is full. Chlorine would take 1 in, so now this valence shell is now full with 8. And so now we have a situation where we have a full one with a positive charge, a full atom with a negative charge. And so because you now have, I'm going to do a little drawing here, because now you have a positive sodium ion and a negative chlorine ion, these two are now attracted to each other because of those charges. And so now you see this kind of lattice where the negative chlorine ion is attracted to the positive sodium ion, is attracted to the negative chlorine, and so on and so forth. And it forms this kind of crystal-like solid of sodium chloride, okay? Now, we'll see the significance of all these positive and negative charges when we start talking a little bit more about water. So that was ionic bonds. So remember, ionic bonds are formed from a positive and negative ions joining together based on their charges. We also then look at covalent bonding, and we look at covalent bonding in the molecules and the molecular components of those. These are going to be covalently bonded molecules in which the electrons are actually going to be shared between the atoms of 2 or more different elements. And these are going to be termed molecular compounds, okay? So if we look at molecular compounds, we have to look at a couple things. So a compound typically is what we would consider, I'm going to type this out here. So a compound is a combination of 2 or more atoms of different elements, okay? So we have a compound here in carbon dioxide. We have carbon and we have oxygen. So that makes us, or gives us, a compound. However, a molecule is simply a combination of 2 or more atoms. So here we have oxygen, and this is O2. We only have one type of atom, but we have two atoms of oxygen. So this is a molecule of oxygen gas. This is a molecule of carbon dioxide. However, carbon dioxide is a compound. O2 is not, okay? So make sure that you kind of understand the difference. And so let's do this. For attendance purposes, let's go ahead and make molecule and compound kind of our code words, okay? Again, make sure that you watch the video. You'll see what you're supposed to do with that, but compound and molecule are our code words today for the attendance. So let me go ahead, we'll clear the drawings. Oops. So if we look at some of the molecular and structural formulas, we can look at the molecular formula, which indicates the number and the type of atoms, okay? So our molecular formula of carbonic acid is going to be H2CO3. Again, molecular formula simply tells us the number and the type of atoms. It tells us that we have 2 hydrogen, 1 carbon, and 3 oxygen atoms. Now, our structural formula, on the other hand, indicates the number and the type of atoms. So it's going to be a little bit more of a graphical representation. It also helps us to indicate the arrangement of atoms within the molecule. So if we again look at carbon dioxide, this is CO2. We have carbon in the middle sharing 2 pairs of electrons with each oxygen atom, okay? Now, what this does then, it allows differentiation of isomers, which if we kind of look at the definition of isomers, it's going to be the same number and type of elements, but they're actually arranged differently in space. And we'll really start to see this a little bit more significantly when we get into our macromolecules. Things like lipids and carbohydrates really start to see a lot of different isomers where we have molecules that have the same chemical formula or same molecular formula, but they start to really have different structures in how they're put together. So we get a chance to see that right here. Here we have 3 molecules, all with the same molecular formula, C6H12O6. Now, normally, when you see what C6H12O6 is, we normally automatically think, yeah, that's glucose. Or if you haven't or don't, you probably will. This is the most common sugar that we typically talk about and is a major fuel for the human body. But we also have several isomers that come off of that. So if we look, again, C6H12O6 on all 3 of these. So they have the same molecular formula. They each have 6 carbon, 12 hydrogen, and 6 oxygen. However, the atoms are going to be arranged differently. You'll notice in glucose and galactose, these basically give us kind of a 6 or a hexagonal shaped, 6-sided shaped ring on both of these. Whereas fructose kind of gives us more of a 5-sided ring or a pentagonal shape. And so again, these isomers are going to have different arrangements of all the same atoms, but they also can have different chemical properties, okay? So there's some differences between those. So now when we look at these types of structures and these type of molecules, the way they bond together, we have to understand the type of bond. And that's where we come to a covalent bond. So a covalent bond is where we share electrons. And so it occurs when both atoms require electrons, okay? So it typically is going to occur in atoms with 4 to 7 electrons in their outer shell. And they're most commonly found in the human body using these 4 elements, which again are the most common elements in the human body. And this is where we use hydrogen, oxygen, nitrogen, and carbon. So if we look at a single covalent bond, this is where we share 1 pair of electrons between the two elements. Okay, so for example, we look at two hydrogen atoms. We have one pair of shared electrons. I believe we show these here coming up. We do. So we have hydrogen gas is going to have one pair of shared electrons. Oxygen gas is going to have two pair of shared electrons, and that's going to give us a double covalent bond. And then we have a third one, which is a triple covalent bond, and this gives us three pairs of shared electrons between the two nitrogen atoms. So if we look at hydrogen gas has a chemical formula of H2. You will notice in here that each hydrogen has one electron. Again, the atomic number of hydrogen is 1, has one proton in its nucleus. It has one electron in its valence shell. However, with hydrogen 2, again, the first shell gets full by having 2 electrons in it. And so in order to have both atoms be satisfied, they basically just share the single electron that they have. And so this is one pair of shared electrons. This is a single bond, and you can see that indicated right here by that single line. This indicates a hydrogen bound to a hydrogen by sharing one pair of shared electrons. Now, if we look at the double covalent bond, again, we have 2 electrons in its valence shell, 2 electrons in its valence shell. We have a total of 6 electrons in this valence shell and 6 in this one. So in order to be satisfied by the octet rule, by having 8 in its valence shell, oxygen really needs to either get rid of or take on 2 electrons. So in this case, what it does, it wants to take on 2. So since both atoms want to take on 2, they just share them. And so here we have 1, 2, 3, 4, 5, 6, 7, 8. And so now both atoms of oxygen are satisfying the octet rule by sharing 4 electrons or 2 pairs. And you see that here indicated by 2 lines between the individual oxygen atoms. And so the same then is true for the triple covalent bond. You have 1, 2, 3, 4, 5, 6. So we're sharing 3 pairs of shared electrons. There's your other 2 for a total of 8. And there you can see an indicated by a triple bond. So 3 lines between the 2 nitrogen atoms. So if we start to look at the covalent bonds and how they're integrated into additional atoms of different elements, we can see how carbon really starts to play into this. Now, what you're going to find with carbon is carbon's kind of this middle road. It's got 4 valence shell electrons, so it really always wants to try to fill its electron by sharing 4 pairs. And so it's typically going to have 4 bonds between it. So if we look at hydrogen here, hydrogen wants to share 1 pair of electrons. So this is a good situation to add 4 hydrogen to 1 carbon atom. This gives us CH4. This is methane gas. And now you can see every atom, hydrogen with 2 in its valence shell, all 4 of them are happy. Carbon has 8 in its valence shell. It's happy. The same thing with carbon dioxide. You can see carbon wants to share or get to 8. So it's going to share 4 pairs of shared electrons, 2 with this oxygen, 2 with this oxygen, and there's 8. And you can see the same thing with ethanol, how we integrate a few hydrogen atoms with an oxygen atom. Okay? So again, just a little bit different way for us to kind of look that over. So now we get a chance to see what a carbon skeleton really looks like. And you'll see these drawn out quite often when you start getting into specifically into organic chemistry. This is where a lot of this stuff comes into play. So when we look at carbon, we can see that carbon can bond in straight chains, okay, down through here. We can see how it can bond in branch chains. We have different branchings and it can look a little bit differently. Or it can be in rings. And so here we have a few ringed structures. And this just kind of shows how we can identify them. We can obviously draw out every single atom that's involved. We can put it here in a straight line, if you will, but normally we can leave the majority of the hydrogen atoms off of there because we can make the assumption that these are all hydrogen unless otherwise indicated. Or we can have this kind of drawing down here, in which case if we do that, each point indicates a carbon atom. There indicates a double bond, and then here you can see at the very end we have our methyl groups. And that goes the same way with our branch chains down here, as well as our ring structures. So when we look at covalent bonds, we still have to look at what we consider the polarity of our covalent bonds. And so some of the electronegativity, some of the ions, some of the electrons are actually going to be shared slightly differently, okay? And so this gives us what we call a nonpolar and polar covalent bonds. So the electronegativity is the relative attraction of each atom for the electrons. And what it does, it determines how the electrons are shared in a covalent bond. Remember, I just said that we can have unequal sharing, meaning that the electrons have a tendency to shift or veer more towards a particular atom. If the two atoms of the if we have two atoms of the same element are going to have equal attraction for the electrons, this is what we call a nonpolar covalent bond, in that there is no polarity. If we have a situation where the electrons are shared unequally, this is where we have a polar covalent bond. So if we look at the periodic table and we look at electronegativity, as we move from left to right across the row, the electronegativity increases. The same is also true if we move from bottom to top, okay? So as we move in the columns, in the rows, we're going to see a change in electronegativity. So for 4 of the most common elements composing living organisms, we're going to see where the greatest electronegativity falls. So we have hydrogen, or I should start with oxygen. Oxygen has a greater electronegativity than hydrogen, which has a greater electronegativity than carbon, which has a greater electronegativity than hydrogen, okay? And so when we look at this then, electrons tend to have obviously a more negative charge. As we look at the electronegativity of an atom, and as that electronegativity develops, it's actually going to develop a partial negative charge. The less electronegative atom tends to develop a slightly more positive charge. And we do this, or we indicate this, by using the Greek delta symbol. And it's going to be followed by the subscript plus or minus, depending on whether it's a little bit more electronegative or a little bit more electropositive. The exception to the rule of a polar bond forming between two different atoms typically is with carbon bonding with hydrogen. Those typically are always going to be electroneutral, if you will, or a nonpolar bond. So let's look at some of the nonpolar, polar, and amphipathic molecules. Again, covalent bonds can be polar or nonpolar. Nonpolar molecules are going to contain nonpolar covalent bonds. So for example, O to O and C to H are nonpolar bonds, whereas polar molecules contain polar covalent bonds. So OH is a polar bond in the polar molecule water. So H2O is a polar molecule, okay? And we'll see what that means here in just a little bit. Nonpolar molecules can contain polar covalent bonds if the polar covalent bond cancels each other out. For example, carbon dioxide. we have a polar bond between carbon and oxygen, but because we have two of them, they basically cancel each other out, and so we end up having more of a non-polar molecule. So I'm going to kind of move ahead just one little slide here real quick. Uh, this is kind of what we're looking at when we look at some of these polar molecules. So here, this is a water molecule. Here we have our oxygen. Here we have our two hydrogen indicated by kind of the white or white marks, basically white bubbles. Again, we have an unequal sharing of electrons. So the sharing of the electron tends to shift more towards the oxygen atom, which means we have a little bit more of a negative charge. So you'll see that Greek symbol there with the minus mark. Here we have the Greek symbol with the positive mark, indicating that yes, we're still sharing electrons, but we're actually having a little bit more of a sharing of those electrons towards the oxygen atom. And because of this, this gives us a polar molecule. So we see where this oxygen atom is going to be a little bit more negative. These hydrogen atoms are going to be a little bit more positive. And we're going to see the effects of what that does here in just a second. So if we look at these intermolecular attractions then, and we look at what these polar molecules can actually do, we have these weak chemical attractions that occur between molecules. These are what we typically call hydrogen bonds. The significance of hydrogen bonds in the human body is that it's important for developing the shape of complex molecules. So for example, DNA and proteins utilize hydrogen bonds between the components of them in order to help maintain their shape. If you think back to what DNA does, or what the DNA structure looks like, it's a double helix, if you've learned that before. And in order to maintain that double helix, we really need to look at the hydrogen bonds and how they hold everything into place. So hydrogen bonds are actually formed between polar molecules. And the attraction is between the partially positive hydrogen atom and the partially negative atom. Okay? Now, individually, these specific bonds are very weak. So if you talk about just one hydrogen bond, we're actually talking about a very weak bond. However, when you start adding a bunch of them together, it actually becomes a very strong bond. And one of the most prolific ways that we study or we look at hydrogen bonds is with water. And by looking at water, it influences how our water molecules behave. So again, we're looking at water here, and it's going to essentially, to a certain degree, kind of attack this glucose molecule, which again has some of these polar bonds between the oxygen and the hydrogen. And so you can see here it's got the electronegativity. Well, we now have the negative oxygen attracted to the positive hydrogen of these glucose molecules. And this is what starts to allow water to break things down. But what it also can do is it also does this. Okay, so this is just a little insect, a little water strider. You'll notice it's sitting on top of the water. And if we scroll back, this is what water does. If we take the positive of oxygen and the negative of oxygen and the positive of hydrogen, we form these hydrogen bonds between all these individual water molecules as well. And by doing that and forming a bond, we basically form what we consider surface tension. And so this is why some insects are actually able to just kind of run or stride across the surface of the water without hitting it and falling down. Anything that breaks the surface plane is essentially able to use weight to kind of break the bonds or displace water. However, because these insects have virtually no weight, they're able to kind of scoot across the top and use their limbs to essentially attach itself to the surface of the water. It's also part of the reason why, if you ever do this, If you take your finger and touch the surface of a pool or water and try to lift up, you'll notice the water kind of sticks to your finger for a little bit before it breaks off. That's the surface tension. It's the water actually forming hydrogen bonds and not being able to release them until something overcomes that bond. And this is where we start to look then at water. Okay. And so water composes 2/3 of the human body by weight. We know water is obviously a polar molecule. It's got one oxygen atom bonded to two hydrogen atoms. And we also know that the oxygen atom is going to have two partial negative charges, which make it overall negative because of the two hydrogen atoms. And the hydrogens have a single positive charge. Okay. And what we also know then is that water can therefore then form 4 hydrogen bonds with adjacent molecules because again of the two partial negative charges formed at the oxygen with the two hydrogen and the individual single positive charges of the hydrogen. Okay. And so if we look at this again, here you have your oxygen, here you have your hydrogen. Again, unequal sharing of those electrons. The oxygen tends to pull it in a little closer. So it makes this a little bit more negative, and it makes the hydrogen a little bit more positive, okay? Just a small amount. But now you get to see how water forms hydrogen bonds between itself, okay? So again, a positive hydrogen with a negative oxygen, a positive hydrogen with a negative oxygen, positive hydrogen, negative oxygen, and a positive hydrogen with a negative oxygen. And this gives us the 4 bonds, the 4 hydrogen bonds between the water molecule. So as we then continue with the phases or with water, we also get a chance to look at the phases of water. And there are 3 phases depending on the temperature. We can have a gas, which is a water vapor. And this is where we have substances with kind of low molecular mass. We can have a liquid. This is where we become water. And this is almost all water in the body. Okay. Or this is how we have most of our water in the body is in liquid form. Liquid at room temperature is basically due to hydrogen bonding. And then lastly, we have a solid. And this is if we drop the temperature and it became ice. So let's look at some of the functions of liquid water. We basically see a lot of these functions within our bodies as well. And so when we look at liquid water and how it transports substances, it also allows substances to dissolve within the water. And this allows the body to actually move these substances a little bit easier, okay? By having, again, ions or different things dissolve, we can actually transport them from point A to point B within the body. It helps to decrease friction between body parts or body structures. So we're looking at lubrication. A great example here would be synovial fluid. So that's kind of an example of lubrication, is synovial fluid that we find between our joints. We also have cushions, or the function as a cushion. And this absorbs sudden forces of body movements. A great example of cushioning is actually going to be your CSF, or your cerebral spinal fluid, because CSF essentially surrounds the brain and a big chunk of the spinal cord. And so it prevents major movements from, or at least smaller movements, from causing significant damage. We know water can be utilized in excretion of waste as we look at urine. So it basically allows certain ions and substances like urea to be dissolved and eliminated in that process. We have cohesion, again, because of hydrogen bonding. It allows the water molecules to create this attraction between each other. And so we have this cohesion of the water molecules, which then leads us to the second part, which is surface tension. And surface tension kind of takes these cohesive forces and pulls them inward at the surface of water. And this helps to cause moist air sacs in the lungs to essentially collapse and expand. And then we also have a surfactant, which is a lipoprotein, and this prevents the actual collapse of our lungs. We have adhesion. So adhesion is the attraction between water molecules and a substance other than water. Okay, so surface tension is kind of this pulling in of the cohesive forces of water, whereas adhesion is actually using this attraction to help bind to other substances. We also have particular temperature. So we measure the kinetic energy of atoms or molecules within a substance, but the principle of temperature is that when we look at water, it's actually hard to change the temperature of. So it kind of helps to maintain a specific body temperature or helps to regulate certain things within the body. And that also kind of ties into what specific heat is. Specific heat is the amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. Water's value is extremely high because it actually needs a lot of energy to break the hydrogen bonds that are formed by individual water molecules. And again, it's kind of because of these that allows us to maintain a specific or a constant body temperature. And then lastly, we have a heat of vaporization. And heat of vaporization is where we require heat for the release of the molecules from a liquid phase into a gaseous phase for 1 gram of a substance. And again, just as what we saw on the last slide, water's value for heat of vaporization is very high because of hydrogen bonding. And again, it takes a lot, or it takes a little bit more to break a lot of these bonds. Again, collectively, they are very strong. But then it also, when we look at heat of vaporization, we look at sweating. And sweating is a process that actually causes an increase in heat so that we generate or get rid of, or condenses and gets rid of a lot of the excess fluid, but also allows us to cool the body. So excess heat is going to dissipate as the water evaporates through the skin, and sometimes even on the skin. Okay. And so then, one of the major characteristics that we look at water for is as a universal solvent. Okay. And so water as a solvent is present in the greatest amount, or a solvent in general is present in the greatest amount. Usually it's a liquid, and also it's oftentimes water. The solute then is what we find present in smaller amounts, and this typically dissolves within the solvent. Now, we look at water as the universal solvent because of the number of substances that we can dissolve in it. And again, some of this comes down to hydrogen bonding. The chemical properties of a substance really determine whether or not it will dissolve in water or whether it won't. And so again, kind of looking at the chemical formula and the structure of a particular molecule. So if we look at substances that are going to dissolve in water, we look at polar molecules first, and these polar molecules and ions. We look at the term hydrophilic, okay? So hydrophilic means water loving, okay? And so when water surrounds these substances, it forms what we call a hydration shell. Now, some of these substances are going to dissolve, but they actually can remain intact. For example, glucose and alcohol. Now, if we look at non-electrolytes, they're going to remain intact, but they do not conduct an electrical current, okay? So these are non-electrolytes. Now, we then have some substances that dissolve and actually dissociate, or what we consider separation. Sodium chloride is one of those examples. It's going to be this salt structure. And if you think about what happens when you put salt into water and kind of swirl it around, salt's going to dissociate into sodium and chloride ions. We also see acids and bases that are also going to dissociate into their component ions. For example, hydrochloric acid will dissociate down into H plus and Cl minus, okay? And these electrolytes, these ions that kind of have this electrical charge, are able to actually conduct a current. Now, we have substances that actually do not then dissolve in water. And these are going to be what we call nonpolar molecules. Nonpolar molecules are hydrophobic, and this means they are water-fearing. Hydrophobic substances requires carrier proteins to be transported within the blood. Because again, blood is made mostly of water. If these substances cannot be dissolved within water, it makes it difficult for water to carry them or get them into different cells. And so they actually need specific channels or transport proteins to be able to get from point A to point B. And examples of these are going to be fats and cholesterol. These are substances that are actually unable to dissolve within water. Now, if we think about what nonpolar is, remember, nonpolar, they don't have a positive or negative charge on the polarity scale. And so because of this, we have no place for the electropositive hydrogen or the electronegative oxygen to come in and try to bond to it and break it up. Whereas when we look at sodium and chlorine, they do have these positive and negative charges. So the electronegative oxygen can come in, bind to sodium, and basically start to pull it apart and break it apart from that crystalline lattice that it formed as table salt. Now, we also then have substances that can partially dissolve in water. And these are called amphipathic molecules. And they typically have both a polar and a nonpolar region. Okay? So when we look at the polar portion of the molecule, we're actually going to find that it dissolves in water, whereas the nonpolar portion is actually repelled by water. Phospholipids here, these are great examples of amphipathic molecules because when we look at the structure and what they do, phospholipids help to make up a lot of the cell membranes of our cells. We're going to find that there's a polar head and a nonpolar tail. The polar head is going to be to the external surface of the cell, and they're actually going to have contact with the water on the outside of the cell as well as the water on the inside of the cell because there is actually a double layer. Okay, it's called the phospholipid bilayer. So we have two layers of phospholipids. The heads are going to be to the external surface of the cell and touching the extracellular matrix. And then we also have the internal layer, and the polar heads are going to be more to the inside part of the cell. Within that area then, between the two polar head sides, we have the nonpolar tails. And these nonpolar tails are going to group together. And these nonpolar tails, again, kind of repel water. And it's because of this that it results in a bilayer of phospholipid molecules. And these are going to make up the membranes of a cell. And so this is kind of what we're looking at, okay? You can see this phospholipid bilayer here, okay? So we got the polar heads on the external surface, the polar heads on the internal surface. We also then have the nonpolar tails inside that phospholipid bilayer. This is where we're going to see a lot of water. This is also where we're going to see a lot of water. And this is where we don't see much water. Again, water-fearing, water-loving, okay? And so this is kind of the structure of our phospholipid bilayer and how we see amphipathic structures that are both water-loving and water-fearing, okay? Here you can see a hydrophilic structure. Again, a lot of ionic bonds. Like water, they have a charge, so water can help to break them down. Here we have a hydrophobic structure. This is non-polar molecules such as fats and lipids. Again, they don't really mix with water. That's why they separate when you mix fats and oils together with water. And so this is actually where we're going to stop for today. And so again, I'll start getting the quiz up for this week's material. I will have one more lecture in regards to chapter 2 for this week, and I will try and get that posted here within the next couple days. Otherwise, again, as far as attendance goes, don't forget about the code word. I'll have that posted, and don't forget to go ahead and watch that video if you somehow did not watch it before you watched today's video.